Therefore, from these two equations, we can redraw the circuit diagram for the KVL and the KCL. And during the on state, we can see the simplified circuit diagram as this will be the V0, which is the output, and we have the V in, and we have the VL, and we have the R, and we have which is the IL. And since it is a closed loop circuit, we now have V in, which is equals to the L, the IL on dt plus the V0, which is now give us the final equation where we have L d IL on dt, which is equals to minus V0 plus the V in. And this we use the KVL, and for the KCL we can redraw the circuit. We have the capacitor, and we have the IL coming in, and we have the resistor. So we have IL and we have IC. From this node we now have the IR, and the final equation will becomes the IL, which is the input, will equals to the C dV0 on dt plus V0 on R, and we now make C dV0 on dt, which is equivalent to IL minus V0 on R when we transpose the formula. And now this is the KCL. So you can see the circuit during on state, the circuit will becomes like this and like this when we compare using the KVL and the KCL. And because for the KVL, this now becomes a closed loop circuit. So from this definition, we said that the voltage in a closed loop circuit will be equals to 0. That's where we derive this equation. And for the KCL, we said that the total current passing through a node, which is this node here, will be equals to the sum of current leaving this node. Therefore, we have this equation here. So it shows how we can use mathematics to derive the equation in a circuit, such as the DC buck converter. Now we are going to look at what will happen during the off state of the DC to DC buck converter. During the off state, now we can have the circuit, a complete circuit, such that the switch will be off, and the switch is nothing but the MOSFET. And when the MOSFET is off, we have the V in. Now the diode will conduct. Therefore, we can have a closed circuit for the diode. And now we have the inductor, we have the capacitor, and we have the resistor. So in this type of circuit, we now will have the switch is off in that case. So no current will flow in this direction from the V in. The only current that will flow inside the circuit is the energy that is stored inside the capacitor. So now we will have all the stored energy from the capacitor that will now flow through this particular circuit. So the current passing through the inductor will be the current that is stored inside a capacitor. And the output V0 will be from the current that is stored inside the capacitor. So we now will have a closed circuit which have the energy supplied by the capacitor. So we will now start to derive this equation, but firstly we can draw the simplified equivalent circuit to make things simple for us. Simplified circuit is very easy when we want to derive the equation for the off state. So we can say the equivalent or the simplified circuit will be, we now know that this should be our diode, and we have 0 volts. That means the voltage input or the source is disconnected, and we have the inductor. We only have this resistor here, so we have the VL and the VR, and we have the 0 volts as the input, and from here we can apply the KVL. And for the KCL, we still have the equation with the equivalent circuit diagram. So from the circuit diagram, we have IL coming in, and we have the IC, and we have the IR, and we can see that this IL is coming in. The equation is same as what we have described using the on state. However, you will see when we start derive the equation, because when we have the on and off state, we can see that for the KCL, the equation remains the same. Therefore, by applying a KCL, since this is a closed loop circuit, we now will have the VI, which is equivalent to VL plus V0, which is our previous equation where we have the voltage source which is connected. And in this case, we know that from the circuit, the V in is equivalent to 0 because we have the input to the circuit which is 0. So we only have VL plus the V0. So we can have 0 is equals to, for the VL, we now have L DIL on dt plus the V0. So we can have make L DIL on dt becomes the subject of the formula. Now we have minus V0, and we can say this is our equation number 3. And for the KCL, previously we know that the IL, which is equals to IC plus IR, the equation will remains the same. So we have IL, which is equals to the IC. We have C dV0 on dt plus the IR. Now we make C dV0 on dt becomes the subject of the formula. We now have IL minus the IR, and we all know that IR will be equals to C dV0 on dt, which is equals to IL minus V0 over the R. And now this will become equation number 4. So this equation is derived from this circuit, and equation 3 is derived from this circuit. So it is simply easy to derive equation using KVL and the KCL of a DC to DC buck converter. So this is how we derive this equation. So in the next step, we will see how we can be able to combine this equation to find the generalized equation for both the on and off state. So in this case, as you can see from this closed circuit, this diode is now be able to conduct. So when it conducts, it forms a closed loop circuit. So in the previous discussion, we can see that when we have the switch is turned on, we can see that this diode becomes the open circuit because the source or the supply, which is coming from the V in, therefore the diode cannot conduct because it is in a reverse bias state. So when the switch is off, that means this diode will now be able to conduct because the energy stored in the capacitor will now be used inside the circuit. However, the voltage across the capacitor and the resistor will be the same, which gives the V out of the circuit. So this V out can now be connected to the load. The combination of the on or the off state in a DC to DC buck converter, we are now going to look at a unified differential equation. And for the KVL, like what we have previously discussed, in terms of the on state, we have the equation L DIL on dt, which is now equals to minus V0 plus Vi, which is the V in. And for the off state, we can simply say we have the L dIL on dt equals to minus the V naught, and we say that the V in is equivalent to 0. And for the KCL, we see that we have C dV naught on dt is equals to IL minus V naught on R, and it is the same for the off state, where we have the V naught on dt is equals to IL minus V naught on R. So the only difference is occurring when the V naught is removed from the equation during the off state. So we can propose this equation such that we have the L dIL on dt is equals to minus V naught plus state, and we have the V in. So the state will be 1 when it is switched on and 0 when the state is switched off. So when this is on, we have this equation where we have 1 times V in will gives us this equation. And during the off state of the DC to DC buck converter, especially the MOSFET, we now will have 0 times V in, which will now gives us this equation. However, for the KCL law, it is the same. So we will just include the state in our combined equation. When the system is switched on and off through the MOSFET, we will produce these two equations for the on state and off state respectively. And since we want to get a unified differential equation, we will now put it in terms of the differential equation form. And since we combine this equation, we are now having a unified general equation as this for the KVL and this for the KCL. So our equation when we combine is L dIL on dt is equals to minus V naught plus the state and the VI, and the second equation is C dV naught on dt is equals to IL minus the V naught on R. So these two equations, we are now going to produce a unified differential equation by making dIL on dt and dV naught on dt the subject of the formula. Therefore, we should now have L dIL on dt, which is equals to minus V naught plus the state, and we have the V in. Now we have dIL on dt is now equals to minus V naught on L plus the state VI on L. So we can simply write dIL on dt, which is now equals to minus 1 on L V naught plus the state on the inductor value times the V in. And also we can have C dV naught on dt is equals to IL minus V naught on R. Now we can divide by the capacitor value in this equation. We have dV naught on dt, which is equals to IL on C minus V naught over RC. And finally we have dV naught on dt is equals to 1 on C IL minus 1 on RC V naught. So we can say finally we now should have dV naught on dt is equals to 1 on C IL minus 1 on RC V naught, and we have dIL on dt, which is equals to 1 on L V naught plus the state over the L VI. So this is the unified combination of the on and off state using a differential equation. And previously we said that by using the state variable such that x is equals to the v0 and the il, and since these two variables is mostly varying in the second, we can now see that we have il and v0 and the v in. Those are some of our variables which are inside the second. So this il and v0 will play an important role when we look at the state space modeling of the system. And now we look at the state space modeling of our system. And now we have dv0 on dt, which is one of the state variables, which is here, and we have dil on dt, which is also another state variables. Now we have, with those state variables, we now have the first one, which is the minus 1 on rc, which is this one, and we have the other one, which is 1 on c, which is this one. So from this differential equation, from the state space representation, we are just substituting the value with respect to the dv0, and which is the il and the v0, and we now have minus 1 on l, which is, and this should be minus v0. So now we have minus 1 on l and v0, and then we have the other state, which is 0 for the off state. And we have now included our state variables, which is the v0, and we have this il. So this state representation is just the same, where we multiply this one with v0, we get this, and we have this one, 1 on c multiplied by il, we get this equation. So similarly, 1 on l multiplied by v0, we get this equation, and 0 times il, we get this equation. And we had 0 and 1 on l and vi. So this now becomes our state space modeling, and for the v0, we can have v0, which is equivalent to 1 or the 0, and we multiply by the v0, and we have the il, and we had, which is the 0 and the s. And from this equation, when we want to derive the state space averaging, we can say this represent the A, this represent the B, this equation represent the C, and this represent the D. We have this equation for the off state, and this equation 1 on L is for the on state. So this discussion is now our state space model, because from the definition of the state space averaging model, it says it represents the average behavior of the system over a switching cycle, which is the 1 and the 0, or the on and the off state. So this switching cycle, when we say a state, we are now representing the switching cycle, which is either 1 or the 0. So with the unified differential equation, we are looking at the state space average model. And since this is our equation derived from our previous second equation, this now represents the averaging model of the state space and the averaging model. And since I want to explain in details why we need the state space model equation, and this is the final solution, but I will explain in terms of the behavior, which is the state space model equation. This is now our state space averaging model. And I will rewrite step by step into how this equation is derived by using the state space modeling. Because how we get the state space modeling, now we can have the state space model equation, and I will describe it in terms of a step by step. So we previously said dv naught on dt, which is equals to 1 on RC minus, and we have plus 1 on C and IL. So this is simply the equation that can be stated in the form of minus 1 on RC V naught, and we have plus 1 on C IL plus 0 VI. And second, we have the DIL on dt, which is equivalent to minus 1 on L V naught plus, we say the state, maybe we can represent it using S, where it is equals to the switching behavior. Previously we say state can be equals to this S, and it can be 1 or 0. So we have S or the state on L, and we have VI, which can now simply be written as minus 1 on L V naught, and we have plus, since for the IL we now have 0 IL, that's why I explained previously that 0 times the IL plus the state over the L, which is VI. So this is how we got the state space equation that we discussed previously. So therefore, in terms of the state space model equation in the time domain, we now have x t is equals to the v naught t, and we have the il t equals to minus 1 on rc v naught, and we have plus 1 on c il, and we have minus 1 on L V naught plus the 0, and we had with the 0, and we have the state on L multiplied by VI. Now we can discuss, let's say, the on state space model when S is equals to 1, which is the state. That means the switch is on. Now we can have xt v naught t and il t, and is equals to minus 1 on rc and 1 on c, and we have minus 1 on L, and we have the 0, and we have the V naught and IL, which is the state variables, plus 0 and 1 on L VI. So this is during the on state, where we can see that the S is equals to 1, and this is our A and this is our B. The off state space model when the S is equivalent to 0. When S is equivalent to 0, we have xt is equals to v naught t il t, now equivalent to minus 1 on rc, 1 on c, minus 1 on L, and we have the 0, and we have the v naught and the il, and now we had with the 0, and we have 0 on L vi, and we can see that the S is equals to 0 because the state space averaging model. We are now going to look at the behavior during the on and the off. So this equation is now is equivalent to xt is equals to v naught t, and we have il t, and it is equivalent to minus 1 on RC, 1 on C, minus 1 on L, and we have the 0, and then V naught and IL. And this equation, since it is 0 and 0, we are no longer going to discuss this because this portion will be equivalent to 0, so plus 0. So during the off state, we will now have the state space model, and during the on state, we will have this model for the on state. So the output is now given as the V naught, which is equals to 1 and the 0, and we have the V naught IL and plus the 0 S, and this becomes our C and this becomes our D, and this D represent the switch, and it can be 1 or 0 or the state. So we are now going to look at the state space average model with the continuous conduction mode. So this state space averaging model combines the on and off state to form the average system over a switching cycle. And now we will look at the state space averaging model under continuous conduction mode. So it says the state space average model combines the on or off state to form an average system over one switching cycle. So we can say that the SS equation becomes, we have the XT, which is the state space model, we have the A average times the XT plus the B average times the UT, and the UT is nothing but the input of the system, and we know that this input is nothing but the voltage input. And how about the XT? XT we defined previously, which is the variable of the state space such that the V naught and the IL. So this gives us the form like what we have discussed previously, so we just only substitute the equation. Therefore we know previously that the A is equals to minus 1 on RC and 1 on C, and we have minus 1 on L and 0, which represent the A, and B we have the 0 and 1 on L. So therefore this is the same as what we have discussed previously. So X T is equals to, we have 1 on RC and 1 on C minus 1 on L, 0, and we can have this XT, and plus B we have the 0 and 1 on L, and we have the UT, and since UT we can just substitute this to here and this to here like what we have discussed previously. So this is now our state space averaging model. Thank you for watching our video. Kindly subscribe to our channel and share this video with your friends so they can also be able to learn.